So the question in this chapter is all about how old is Earth. And so we want to talk a little bit about the tools that scientists use to figure out the age of the Earth. There's two types of dating. We've already talked about relative dating, and much of the early part of this section is about relative dating. Basic principles, the law of superposition says the older rocks are on the bottom when you see a strata, layers of rocks that are undisturbed. And of course, the youngest have been deposited on the top, just like laundry in your laundry basket. There are also index fossils, which can be used to show the approximate ages of rocks. Some fossils lived in a very brief period of time, and they're very unique looking, so when you find that fossil in a rock, you know the age of the rock layer. Rock layers are not undisturbed. There's so many things that have happened over time: earthquakes, faults, flooding, erosion, etc. There are a lot of unconformities. We saw 3 in the Grand Canyon. There's a gap in the rock sequence that happens. Sometimes layers have been eroded away. Sometimes no deposition occurred. Or earthquakes or plate tectonics have caused the ground to be uplifted. But what if you want to know the exact age of a rock? Geologists who want to know the exact age of a rock can use absolute dating. Absolute means an exact or definite time. Everything in the planet is made of atoms. Everything in the universe is. And the defining characteristic of an atom is the number of protons. Now, this is a basic chemistry lesson you probably remember. The number of neutrons can vary from one carbon atom to another, or from one hydrogen atom to another. These are called isotopes. So notice that there are isotopes of hydrogen, helium, lithium, and sodium. The number of neutrons can vary. And over time, some of these atoms may actually turn into a different type of atom. The original atom is a parent, and the new form of atom is called the daughter. Atoms that can do this are called radioactive, and this is a description of radioactive decay. So, half of parent atoms turn into daughter atoms once the object has reached a certain age. Like every year on your birthday, you turn into a different age. So parents and daughters can tell us about the age of a rock. There's a process called half-life. A half-life is the time it takes for 1/2 of the parent atoms to turn into daughter atoms. And different atoms have different half-lives, vastly different. Some half-lives are more than 4 billion years, others 6,000 years. Actually, there are some that have half-lives of seconds. So scientists figure out which atom is best to use to determine the exact age of a rock. Potassium-40 is an isotope of potassium. You may know potassium. It's an element in your body. We eat bananas to get potassium, for example. But the radioactive potassium-40 has a half-life of 1.3 billion years. So it can be used to date rocks older than 100,000 years. Uranium-238 has a half-life of 4.5 billion years. That's the age of our planet. The half-life of carbon-14 is known to be 5,720 years. Why do you think it's a good element to use to date fossils and some rock? Shorter half-life definitely means a more accurate age. So radiometric dating, or using the radioactive decay process, we can use the half-life of atoms to figure out the age of rock layers, and this gives us an absolute age. Scientists have used this absolute dating to figure out the age of the Earth. By counting the parent and daughter atoms in some very old rocks, scientists say that the solar system, including Earth, is about 4.6 billion years old. That's a lot of birthdays. Before this method was invented, some people believed the Earth was only 6,000 years old. Let's look at an example. So a scientist knows that half of the parent atoms will turn into daughter atoms every 10,000 years. So if originally there's 16 milligrams of parent atoms, 10,000 years go by. Half of the 16 milligrams of parent atoms have turned into daughter atoms. Half of 16 is 8. So there are 8 milligrams of daughter atoms now, and there are 8 milligrams of parent atoms left. Check your math. 8 plus 8 is 16. Then another 10,000 years go by. Half of the 8 milligrams of parent atoms turn into daughter atoms. Half of 8 is 4. Now there are 4 milligrams more daughter atoms. Add this to the 8 that was already formed. You have 8 plus 4 is 12 daughter atoms. And there are only 4 milligrams of parent atoms left. Check your math. We started with 16 milligrams. 4 are still parent atoms, but we've been through 2 half-lives. So now we have 12 daughter atoms. Then another 10,000 years go by. Half of the 4 milligrams turn into daughter atoms. So now there's 2 more daughter atoms. Add this to the 12 that's already formed, and now you have 14 daughter atoms and only 2 milligrams of parent atoms left. Check your math. 14 and 2 is 16. So scientists can compare the number of parent atoms to the number of daughter atoms. The more daughter atoms there are, the older the rock is. This tells them how many times half the parent atoms have turned into daughter atoms. In this example, each time this happened, 10,000 years had gone by. So if it had happened 3 times, then the object is 3 times 10,000, or 30,000 years old. So notice in the diagrams, we had all 16 radioactive. Half of them decayed in the first half-life. Half of those decayed, and then half again of those. So every half-life, half of what remains will decay. So here's a little quiz for you. Which method is used to figure out if rock is older or younger than others? Relative dating. But what do we call the method to determine the exact age of Earth? Absolute dating. And that is what radioactive radiometric dating is all about. It's a great tool. Fill in this table. If you have a rock with 20 milligrams of a parent isotope, and 20,000 years go by, and now you're down to 10 parent and 10 daughter, would you say that's 1 half-life? Yes. Now what happens when 40,000 years have gone by? What are you going to fill in for parent isotope? Half of 10 is 5. That means you need to add 5 to the daughter column. So there's your final. Good job.